fractions, guys, is not a calculus topic. Okay, so let me just show you what partial fractions is. In Algebra 1, if you had two problems like this, okay, could I combine it into one fraction? Do you know how to combine it into one fraction? Yes. Okay, if you combine it, you need a common denominator. Do you agree? And that common denominator would be x minus 2 times x plus 5. Do you agree with that? Okay, well, this one already has an x minus 2. So to get this one to have an x plus 5, then what you'd have to do is multiply the 7 times x plus 5, right? If you multiply the bottom by x plus 5, you'd have to multiply the top by x plus 5, right? And on this fraction, you already have an x plus 5, but to get an x minus 2, you'd have to multiply by x minus 2. Well, if you multiply the bottom by x minus 2, then you certainly need to multiply the top by x minus 2, okay? If I try to get this into one fraction, what I would get is 7x plus 35 minus 3x plus 6 all over x squared plus 3x minus 10, if I'm doing that right. And that's equal to, let's see, 7x minus 3 is 4x plus 35 plus 6 over x squared plus 3x minus 10. Do you agree that that's right? Okay, so what we're going to do today is we're going to agree that this is equal to this. Do you agree with that? Okay. And so today on your first problem, if you look, my first problem is the integral of 4x plus 41 over x squared plus 3x minus 10. And that problem, if I try to do u substitution, okay, if I said this was my u, I'd say the derivative of this is 2x plus 3. And you'd say, okay, on the top, if you divide by 2x plus 3, do your x's cancel out? And they don't. You could be like, well, I really want 2x plus 3, so I can make it 2x plus 3. But it becomes very complicated, okay? And what we're going to talk about today is if your denominator factors out, then it's probably a partial fractions problem. It's probably not this, do you really want it, then put it there kind of thing, okay? On your notes, I really wanted it, so I put it there. But you can see what a mess it becomes, okay? So if you want to look at it, you can look at your notes. The notes I'll post tonight, okay? But what I want to show you is if your denominator factors out very nicely, which this one does, okay? This one factors out to this, okay? Then you want to use partial fractions. And why is partial fractions useful? Because if this big old fraction, okay, is equal to the sum of these little fractions, what does that mean? That, yeah, it's a buy one, get one free problem. Do you see that? And this answer would just be the 7 ln of x minus 2 minus 3 ln of x plus 5. Of course, you need to check, make sure that x's cancel out. So I'd say this is my u. The derivative of x minus 2 is 1. Yes, my x's cancel out. This is my u. The derivative of x plus 5 is 1. Yes, my x cancels out, and that would be my answer. Okay? So it's much easier if you could divide it into two partial fractions. This is called partial fraction decomposition, is what it's called. Okay? And so what we're going to do today is I'm going to teach you how to do partial fraction decomposition. I'm going to say, if you start from this problem, how do you go from this fraction to this right here? Okay, and we're going to do it together. So let me show you how to do it. Okay, so remember, we don't know the answer. So let me just start with 4x plus 41 over x squared plus 3x minus 10. And I think this is your first problem. You can start doing it on your notes if you'd like to write your notes. Okay, the first thing you do is you say, hey, this down here factors into, I'll write it, x plus 41. It factors into x plus 5, or x minus 2, x plus 5, okay? So it factors into that. And I'll say, okay, if that factors into that, then one of my denominators is going to be x minus 2, and another one of my denominators for these partial fractions is going to be x plus 5. Okay, and then what you say is, you say, if this is linear, linear means the power here is 1. If this is linear, then you just put a letter A there. If this is linear, then you just put a letter B here. Now, just be careful. If they're linear and they're different, this is what you would do. If they're linear and they're the same, so if you had x minus 2 and x minus 2, it's going to be a little different. I'll talk to you about that in a second. But right now, if they're linear and different, you just put A and B. Okay, and then what you do is you try to get a common denominator over here. Okay, so my common denominator is going to be, if this makes sense, my common denominator between these two problems is going to be x minus 2 times x plus 5. Okay, that's going to be my common denominator. You try to use the lowest common denominator. As a matter of fact, your common denominator is always the same as this denominator. Okay, everybody good with that? Okay, so that's my common denominator. Well, if this is x minus 2, how do I get this to be x minus 2, x plus 5? If I multiply the bottom by x plus 5, then I need to multiply the top by x plus 5. Okay, on this side, to get a common denominator of x plus 5 times x minus 2, well, there's already an x plus 5, so if I want an x plus 5 times x minus 2, then I have to multiply the bottom by x minus 2. Well, if I multiply the bottom by x minus 2, then I also need to multiply b times x minus 2. So do you agree with me that this right side that I've just done right here is the same as 4x plus 41 over x minus 2 over x plus 5, right? I got a common denominator. Okay, that's what they're equal to. This, what I was hoping was, so let me kind of get rid of all of my extra stuff here. Okay, what I was hoping was to change this, oops, I guess that stays, to change this fraction into two easy fractions so I can easily integrate. Okay, remember this is not an integration problem yet. All right, I just want to change it into partial fraction decomposition. Okay, and so what I've done here is true, right? Everything is true. If this denominator is equal to this denominator, what does that mean this numerator is equal to? That numerator. So I have this new algebra problem, and it's 4x plus 41 is equal to a times x plus 5 plus b times x minus 2. And this is actually what we call an identity. Okay? What an identity means is that if I plug in any value for x, this is going to be true, as long as I'm consistent about my x, right? So if I say x is 5, then this side is going to be equal to this side, as long as I say x is always 5. Okay? Now, a and b are going to be unique numbers. Okay, so a and b are unique. Okay, they have unique values, but the x's will not. The x's can be any real number in the universe, all right? And these equations will still hold true. So what I'm going to try to do is solve for my a and b, because if I can solve for a and b, then I'll have my partial fraction decomposition. Okay, so I'm going to use this equation to solve for a and b, knowing that x can be any number. So what I want to do is, while I can pick any number for x, I want to pick a good number, okay? Because if I pick a good number, it'll make my math easier. So if I'm trying to solve for a and b, let me try to pick x equals negative 5. See if you can see why I pick x equals negative 5. So let me just try. I'm going to say x is equal to negative 5. And remember, x can be anything I want it to be. So that will make this problem, this equation, 4 times negative 5 plus 41 is equal to a times, negative 5 plus 5 is 0, plus b times negative 7. You guys see I'm just plugging in negative 5 into this equation. That's an identity. And this is going to give me negative 20 plus 41, which is 21, plus 0 minus 7b. So what's my b going to be equal to? Negative 3. And let me go back up here. Remember, my b is a unique number, so I'm going to replace this b here with negative 3. And guys, I kind of know the answer. Was the number on top of the x plus 5 equal to negative 3? Check that out. It's working out, okay, because I knew the answer. All right, let's see if I can figure out what a is. So come back down here, and I need to find a good number for a, okay? And again, I could pick any number. If you really wanted to, you could pick x as 212, okay? I mean, I really want to, but we just don't have the time, all right? But what's a good number for x equals, besides x equals negative 5? X equals 2, because it'll wipe out this b and I could solve for a. Wait, I just want to make sure you guys know, if I wanted to at this time, I could put in b equals negative 3. It's not real helpful, but I could if I wanted to, because your b is unique. I've already figured out what b is, okay? So I could put it in, but I don't think it's going to be that helpful here. So x is equal to 2. Okay, plug it back into this equation. I'll get 8 plus 41 is equal to 7a plus 0, right? So that gives me 49 is equal to 7a. So what's my a equal to? 7. Come up here. My a is going to be 7. And do you see I got the exact answer as this 7 over x minus 2 and 3 over x plus 5. Okay? So at this point, after you decompose it, and we talked about this, after you decompose this fraction, okay, then if this fraction is equal to this fraction, then now you can use your calculus. That means the integral of this is equal to the integral of this plus the integral of this, and it becomes an easier problem. Okay, are you good with that? All right, let's do your second problem. So I've already integrated that, so I'll leave that for you guys to finish up. Okay, now how do you know when you use partial fractions? Okay, when the denominator is factorable. If your denominator is factorable, you want to think about partial fractions, all right? All right, is this denominator factorable? They factored it for you, okay? Like, how much easier can you get? Does that make sense? They factor it for you, so it's factorable. So what you're going to do is don't do the integration problem first, okay? Do the partial fractions problem first. So I told you this before. This is not a calculus. This is not a calculus exercise, okay? All you're doing is you're taking this thing. Don't worry about the integration, okay? Kids who leave the integration in, you get all messed up because you're like, wait, I'm supposed to integrate at the same time doing partial fractions. You're not going to be able to do it, okay? We're just doing the partial fractions, okay? So what you're going to do is you're going to decompose this thing into two fractions, okay? One fraction is going to have an x plus 1 on the bottom. The other fraction is going to have an x squared plus 4. Pretty easy, right? If this is linear, then it's just one number on the top, so I'll call that number a. If this is quadratic, then actually you need a bx plus c. Okay, I mean, any letter you want. You could call it cx plus d or dx plus e. Does it make sense? You just need to figure out two letters, but they have to have an x here. Okay, so I'm going to call it bx plus c. Why? Because it's a quadratic. Now, it'll change in a second on the third problem. I'll show you why. If you have repeating linear factors, then you do something different. But this is not linear and is totally different from this. We don't have repeating linear factors, so this is how you'll do this. Okay, if it's quadratic, you'll put bx plus c. Okay, so we're going to do the same thing. What we're going to do is we're going to try to get a common denominator on this right side. That common denominator, okay, strategy-wise, should look exactly like this common denominator over here. Okay, so I'm going to copy this denominator over here. But it's basically the common denominator between these two fractions. All right. If I have an x plus 1 down here, what do I need to make this x plus 1 times x squared plus 4? X squared plus 4, right? Well, if I multiply by x squared plus 4 on the bottom, well, I certainly better multiply by x squared plus 4 on the top. All right? Okay, let's look at the second term. The second term, I've got an x squared plus 4 on the bottom. What do I need to get this common denominator? X plus 1. Well, if I multiply by x plus 1 on the bottom, be careful, guys, this is a quantity up here. I better multiply this quantity by x plus 1 on the top. So what I get on the top is a quantity, bx plus c times x plus 1. Okay? So what I have is 7x squared plus 5x plus 23 all over x plus 1 times x squared plus 4 is equal to this whole fraction here. All right, we're doing partial fractions. We're trying to figure out what a, b, and c are. If these denominators are equal, what does that mean about these numerators? They're equal. So that's my identity. So let me write my identity. Make sure you understand it. This is the identity equation that I'll be working with right here. Now, resist the urge to distribute. I know you can, but that prevents you from picking a good number. It's hard to see a good number when you distribute. Okay, so at this point, guys, do not distribute. And what you're going to do is remember, this is an identity. And what that means is every x that you pick will work for this problem. Okay, you just need to pick a good number. But you really could pick a bad number and it would still work. If you picked a bad number, do you see that you have 3 unknowns, a, b, and c? You just need to get 3 equations. So you pick 3 bad numbers, you have 3 equations, 3 unknowns, you solve simultaneously, just give you a bad day, basically, okay? But you'll still solve for a, b, and c. Okay, let's see if we can pick some good numbers though. What's a good number for x? Okay, -1. So let's try it. If I put in -1, I'll get 7 times -1 squared, which is 1, minus 5 plus 23 is equal to a times, well, -1 squared will just be 1. So that's going to be a times 5 plus, and if I put -1 right here, it's just going to be 0. Right? That was a great number, actually, because this gives me 25 is equal to 5a. Did you guys get a is 5? Okay, now watch what I do. If A is 5, A is unique. That means this is 5. This A right here, guys, you can change it to 5. It may or may not help you, but you can change it to 5. It also means when you go all the way up here, let me take away all this gibberish I have here. It means when I go all the way up here, I've actually figured out what my A is, okay? My A is actually 5. So I can come up here and say A is 5. I'm halfway done with the problem. Well, I've got one term anyway. Okay, let me go figure out B and C. So come back down to your identity. What is another good X to pick? 0. The reason 0 is good to pick is because when B gets multiplied by 0, do you see the B wipes out right here? Okay, so let's put in 0. So what I'll get is 0 plus 23 is equal to 5 times 4 plus C times 1, I think. So that gives me C is equal to 3. Can someone give me a check on that? Maybe not. Okay, C is equal to 3. So that means, guys, I can come here and I can say C is equal to 3. That may or may not help me, okay, but I don't have to just have a constant here anymore. And I can come all the way up to my original problem and say this C is equal to 3. I'm almost done. I just need to figure out what this B is, okay? Let's go back to my identity and figure out a B. What's another good number for X? I'm kind of out of good numbers, okay? But guys, remember, I can pick any number I want. So I've picked 0. I've picked -1. What would you like to plug in? 1. Do you guys see that? You can plug in 212. Again, it'll work, okay? But it's going to be bad, okay? So let's do X equals 1, okay? So guys, if I put X equals 1, what I'll get is 7 plus 5 plus 23, plugging it right back into the identity. It's equal to 5 times 5 plus, I'm doing X equals 1. That's going to be 1B plus 3 times quantity 2. Okay, on the left side I have 12 plus 23, which is 34, I believe. Is that right, or 35? 35. Okay, it's going to be 35 is equal to 25 plus, I'm going to distribute this 2. That will be 2B plus 6. So that will give me 10 minus 6. 4 is equal to 2B. Can you give me a check? I'm getting B is equal to 2. Okay, if B is 2, I'm done with my problem. Come up here, and B is 2. Okay, now why is this helpful? Let's do the calculus. Guys, I have not done any calculus at all. Okay, all I did was say that this problem is the same as the integral of 5 over x plus 1 plus 2x plus 3 over x squared plus 4. And to be a good girl, I probably want to put my dx's in. Okay, this problem is terrible, but this problem is just half as terrible. Okay, so let's take a look at this. Hopefully I plugged in my numbers right. Make sure you plug in your A, B's, and C's right. Another common problem students will do is they'll put the A in for B and the C in for A. You know what I'm saying? And if you mix it up, it won't be right. Okay, this is pretty easy, right? This right here is just 5 times the ln of x plus 1. Why? Because if u is equal to x plus 1, the derivative of x plus 1 is 1, and the x's cancel out. 5 divided by 1 is 5. Okay, over here, though, the derivative of x squared plus 4 is 2x, and do my x's cancel out? No, but they would if I split it up. Do you guys know what I'm saying? If I split it up into 2x over x squared plus 4 plus 3 over x squared plus 4. Okay? And this is really a good deal because I thought I got to do one problem. And then I thought I got to do 2 problems. But, oh boy, I get to do 3 problems. What a deal. Okay, what a deal. Okay? And these are actually not too bad. The last one's probably the worst. Okay, but they're actually not too bad. This is my u. This will be divided by the derivative. That's going to be 5 ln of x plus 1. If this is my u, the derivative of x squared plus 4 is 2x. That cancels out to 1. So this will be 1 times ln of, well, I don't even have to put the 1 times. So ln of x squared plus 4. Okay, this one, what's it going to be? Arctangent. Okay, so this one's going to be, and I'm just going to write this answer for you, but you guys can figure it out. It's going to be 3 over a arctangent of u over a plus c, and your u here is going to be x, and your a here is going to be 2. Okay, and I'll let you guys plug that in. All right, And that's the answer. All right, I want to go to the last problem. Okay, it is a partial fractions problem. How do you know? The bottom is factorable. How do you know the bottom is factorable? They factored it for you, okay? So what we're going to do is we're going to not do the integration problem first, guys. Pause from the calculus. I know you love calculus, okay? But it's going to confuse you if you're going to try to do the calculus the same time that you do the partial fractions, okay? Now, this problem is a tricky problem. Why? Because this denominator is actually has two linear factors that are the same, okay? When you have two repeated linear factors, okay, it changes the game a little bit, okay? What you have is one denominator is x plus 1, and the other denominator is x plus 1 squared. I mean, if you think about it, like if I had, I don't know, it's probably a bad example. I'm not good at making up examples, but if I had 1/3 and 1/9, wouldn't this common denominator still be 9? Does that make sense? Even though you want it to be 27, okay? So basically, this is the same thing. When you break it up, one's a squared and the other's like just not with the squared, okay? Now, because they are all linear factors, this will be A. Well, this is not repeated, so this is definitely just A on top, okay? The x plus 1, because it's linear, it would just be a B, okay? The x plus 1 squared, even though it's a quadratic, because it's a repeated linear factor, it just gets a C, okay? Now, I got to tell you, if you're confused by this and you call this Cx plus D, you will be fine, because what will happen is you're going to get this value. This is going to turn out to be 0, and this value will be some number. Does that make sense? When you do the equation thing, you'll get the same thing. You'll just have made your life a little harder, okay? But you'll get the same answer if you don't remember this, okay? So that is what you do when you have repeating linear factors. We're going to do the same thing here, guys. We're doing partial fraction decomposition. Now, be careful. The common denominator here is not multiplying all these three together because we have one that's repeated, okay? So look over here for the common denominator. This is going to be the common denominator over here, x times x plus 1 quantity squared. What a lot of students do wrong is they make it x times x plus 1 times x plus 1 squared. Then you get a cubic on the bottom. Does that make sense? And it becomes huge, and it doesn't really work. Okay, so you really want to just make sure your denominator matches with this denominator over here. Then you do the same thing. You say this is a common denominator. So if you already have an x, what do you need here? X plus 1 squared. If you multiply by x plus 1 squared on the bottom, make sure you multiply by x plus 1 squared on the top. This b right here, you have an x plus 1 in the denominator. Okay. What you really are missing here is two things, an x and an x plus 1. You guys see that? So the b is going to be multiplied by both x and x plus 1. And so I'll put this term right here. That's bx times x plus 1. And finally, the c is really just missing an x. So this would be plus cx. Okay? This right side is equal to this left side. Make sure you understand, I have not done any integration so far. All I'm doing is trying to break up this fraction into three different fractions. Okay. I'm also going to take out all these little extra things because this actually is what I don't need these anymore. Okay, so let me pull these extra things out. Okay, so this fraction is going to decompose into three partial fractions, and this is how I'm going to do it. Are my denominators the same? Yes. Okay, that means what's true about my numerator. They are the same. So I'm going to set up my identity here. Okay, and identity means that any real number for any real number of x, okay, this left side is equal to this right side. My goal is to solve for a, b, and c. I have three unknowns. All I need are three equations. I can make up any three equations using any x numbers I want. But what's a good number for x? 0. Okay, let's try 0. Here's 0. Let's go ahead and plug in 0. This will be 0 plus 0 plus 6 is equal to a times 1 plus b times 0 plus c. Ooh, a is 6. Did you guys get a is 6? Okay. What's another good? Oh, well, let me go ahead and replace this. A is 6. Oops, sorry. A is 6. And then come back up here, and I've already got 1/3 of my terms. Pretty good. All right. What's another good number for x? All right. Let's try x is -1. If x is negative 1, I'll get 5 times positive 1 minus 20 plus 6 is equal to, this term will wipe out, this term will wipe out, this will be negative c, so negative 20 plus 11, is that negative 1? Negative 20, or is that positive 1? No, that's not even, is that 9? Okay, is it negative 9 though? Okay, it's negative 9 is equal to negative c, so did you get c is equal to 9? Okay, so if your c is 9, you can come up here to the identity and just take the c and put 9. I also know that up here, my c is 9. You can already put c as 9 up there. All right, now I just have to find my b. What's another good number? Yeah, I'm kind of out of good numbers, but remember, I can plug any number I want, and if I could choose a number, I would just be like, I just want to do 1, okay? So this is where being lazy is actually helpful, okay? So if x is equal to 1, then this will be 5 plus 20 plus 6 is equal to 6 times, if I put a 1 in here, that'll be 4, right? Because 2 raises a squared, okay? Plus b times 1 times 2 plus 9. That's x equals 1. So 26, is that going to be 31? Okay, is equal to 24 plus 2b plus 9. 31 minus 23, is that negative 2 is equal to 2b? I don't really know. Is b equal to negative 1? Yeah. Okay, b is negative 1. If b is negative 1, oh, actually, I'm already done. Just go all the way up, and b is negative 1. Okay, so this problem, this integration problem is actually equal to the integral of 6 over x plus the integral of negative 1 over x plus 1 plus the integral of 9 over x plus 1 quantity squared. And I technically should put a dx in each one of those. Okay. And every single one of this is a U substitution problem. The first two are LNs, and the second one is just a regular U sub. Okay, so let's see if we can do this. Make sure I copied it all right. And let's go ahead. The first two are pretty easy, right? So let me just do the last one for you in case we run out of time. On this last problem, what's your U going to be? X plus 1, right? So your du is going to be dx, or your dx is going to be du. And so what I'm going to do is I'm going to replace two things, my dx and my u. So this becomes 9 integral of 1 over u squared du, okay? But that's really 9 integral of u to the negative 2 du. Okay, it should be an easy reverse power rule problem for something that's on my pink sheet, all right? That's going to be add 1, divide by negative 1. So that's going to be negative 9 u to the negative 1 plus c. That's going to be my answer right here. But u is actually x plus 1, right? So this right here will be negative 9 over x plus 1 plus c. Okay? So my answer is going to be 6 ln of x minus ln of x plus 1 minus 9 over x plus 1 plus c. And that's a great answer. And it's the right answer. Okay? Any questions on partial fractions? Do you like it? Yeah. It's kind of a cool thing, right? I don't know who invented it, but it actually was a very clever method to use.